so we started the idea of a limit, and we kind of went about this idea by talking about graphs. So maybe a graph of someone driving to school. Normally, it doesn't look like a straight line, but we assumed that he was going the same rate the entire time, and we found this very constant sort of graph. But in reality, the graph is going to look like this, where we have a curve in the middle. And we figured out, though, even though it was kind of hard to find the instantaneous velocity at a specific point, there were ways that we could approximate the velocity by the average speed, or by connecting the dots between the beginning and end. And we also realized that if we chose dots closer to our point and closer, we could get something really, really, really close to the velocity. The idea of that shrinking window is kind of the theory behind this thing called a limit. It's not something that we can exactly say, but we can expect something to be. Okay, so we took a look at this function, 9 minus x squared over 3 plus x. We found its domain and found it was kind of wonky around -3. And we wanted to figure out what actually happened at -3. Okay, to do that, we plugged in x values that went closer and closer to -3 on the left-hand side. So to the left of -3. And we found that, okay, as x approaches -3 from the left, the function f of x, or the y values, approach 6. Now, instead of writing that whole big thing, we basically abbreviated this as the limit as x approached -3 from the left with the negative sign of our function was equal to 6. And we called that a one-sided limit because we were approaching it from one side. Okay. We did the same thing, but on the right-hand side. So we plugged in numbers very, very close to -3, our x values, and we got y values that also got very, very, very close to 6. We said the limit as x approaches -3 from the right-hand side of our function equaled 6 as well. Since the left-hand limit and the right-hand limit were the same number, they were both 6, we were able to, we weren't able to do this. But let's continue on from here. Okay, the left-hand limit and the right-hand limit are the same. As we approach from the left, the y values approach 6. As we go from the right, the y values also approach 6. We can set up what we call a two-sided limit. So let me write that down, a two-sided limit, which basically says as we go from the left-hand side, we get one number. As we go from the right-hand side, we get the same number. And we can say, as x approaches -3, our function gets closer to 6. So no from the left or from the right here. Another way to write this is the limit as x approaches -3 of our function equals 6. So that's how we write our two-sided limit. All that's saying is the left and right are the same number. Okay, let's take a look at what this function actually looks like and see if it makes sense to us. The function, if we draw it, actually looks like this. So it looks like a straight line, but there is a hole at -3. You wouldn't think a rational function looks like this, but most rational functions where you can like cancel out the top and bottom look like this, a straight line with a hole in it. And well, taking a look at this, we plugged in x values from the left-hand side, getting closer and closer to 3. And as we went from the left and got closer to -3, the y values got closer and closer to 6. Okay. As we went from the right and got closer x values to -3, our function also got closer to -6. Even though our function, well, it's not defined at -3, we have something that we can expect our function to be, which is 6. Okay. Any questions about the graph? Okay, I have what is happening here. The function doesn't exist at 6, but it's getting closer and closer to 6. That's where we would expect the function to be. Okay. It's a hole because let's take a look at our function here. Essentially, the top is 3 minus x, 3 plus x, if I factored it, right? We have 3 plus x here. Okay, these guys cancel and we're left with 3 minus x, right? Now, I can't say that these two functions are equal because they have the same domain, right? So the domain of this function is everything except -3, right? I have to keep that domain here. So basically, this function is the graph of 3 minus x with the constraint that x can't be negative. Oh gosh, -3, sorry. Does that make sense? So that's why the graph looks like that. Okay. All right, that's a good question. Okay, so let's take a look at more limits. We're not actually going to calculate any today, but we're going to take a look at how to figure out what limits are by just taking a look at the graph of a function. Okay, let's flip our page to example 2. Okay, so here we have a function. It looks a little funky. This is an example of a piecewise function. Okay, piecewise. Okay, and what that means is our function is split into different pieces, okay? So for different x values, we have a function, then another set of x values, okay? Okay, first of all, let's try to graph what this function looks like, okay? So g of x is 4 when x is less than 2, and it's x squared when x is greater than or equal to 2. How would I go about even drawing this function?
When we look at the first part, which is when x is less than -2, we know that's going to be a whole because it doesn't equal -2. And since it's going to be less than, it'll be from -2, we go from -3, 4, and now be equal to 4.
Good. So let me kind of go slower about, I'll just kind of step through what Jude said here. So let's start with the 4. We know that when x is less than 2, -2, we're at 4. So the function takes on the value 4. Let me draw a different color here. Do blue. Everything less than -2, our function is 4. Okay. I think Jude also said we're going to have a hole here because, well, it's not 4 when x is equal to -2, right? So we're just dealing with that first term here. Okay. Then it says, okay, after -2, the function takes on the value of x squared. Okay, so let's go to the right of x equals -2. So we're essentially dividing the graph into 2 different pieces. Okay, I know what x squared looks like. That's a parabola, right? So I can literally just draw my parabola. Okay, we've got 2 and 4. I'll go back to -2 in real quick. But we've got a big parabola going on here. Okay. What's the value of my parabola at -2?
You can circle it. It's 4.
It's 4, right? So we can actually fill in the circle because, not because of the top part, but the bottom part is telling us that we can fill in -2, 4 as our point. Okay. Any questions on how to get this graph? Nice. Okay. So we got a parabola, we got a constant function. What do you think might be one of the points we might be interested in a limit being to -2, right? That's kind of where the function like, oh, did you say 2?
I meant -2.
Oh, okay. Okay, yeah. -2 is where the function like switches, right? So let's try to see the limits. If I want to find the limit at x equals -2, we have to look at the left and right, right? We can't just do the limit because the limit tells us we can't do a 2-sided limit because a 2-sided limit means the left hand and the right hand are equal. Let's do the left hand side and the right hand side and see what they equal. So the limit as x approaches 2, let's start from the left of g of x. Okay, let's see what this means. Okay, this is saying that as the x values get closer and closer to -2, okay, so we're looking at the x values, we're going to see what the y values do. So what are the y values getting closer to? Well, what are they getting closer to?
or when never reaching it.
For, yeah, I guess not reaching it because we're not actually reaching x equals -2. So I like that explanation. We're getting closer. The x values are getting closer to -2. The y values are getting closer to 4, right? Actually, they are reaching 4, aren't they?
It just stays.
They just stay 4, right? If I plugged in -3, I would get y equals 4. If I plugged in -2.5, y would be 4. -2.01, y would be 4. So we expect the function to be 4 around -2 on the left-hand side. All right, let's go from the right. All right, so we're talking about as the x values approach -2 on the left-hand side, what are the y values approaching? 4, right? If I plugged in -1, I'm getting 1. Okay, that's not close to 4. If I plugged in -1.5, I'm going to get something around 2, getting a little closer. If I plugged in -1.9, I would get something really close to 4. If I plugged in -1.999, I would get something extremely close to 4. And I would expect this function to reach the y value 4 if I'm going from the right as well. Okay. Okay, do I have a two-sided limit? Yes, right? The left-hand and right-hand limits are the same. So I can say that the limit as x approaches 2, no symbol at all, of our function is equal to 4. Okay. Any questions? Good. All right, let's try a different function. It's going to be slightly different. I'm going to talk about how the limit may or may not be different. Okay. Oh my gosh, I can hear my voice. That's really annoying. There we go. Okay, so we're going to draw this function. We're still 4 when x is less than -2 and x squared when x is greater than -2. How is this graph going to be different than the top one? Yeah, right. We don't have an equal to -2. So our function isn't actually defined at -2, which means it's going to look the exact same as our function before. So let me just draw some points here. It's going to look like a parabola and a line. But as I heard in the class, we're going to have a circle, an open circle at -2. Okay. So before we even go into limits, what is g of -2? What do I get when I plug in -2 into g? Nothing, right? We actually say this doesn't exist, does not exist. Okay, because the function doesn't have a y value when x is -2. Okay, so I guess we should be interested in -2, what our function should be here. Let's take the limit as x approaches -2 from the left of g of x. Okay, so as I plug in x values close to -2 from the left-hand side, like -3 or -3.5, what are the y values approaching? 4, right? If I plug in -2. I don't know, 0001, I would get something really close to 4. I'm expecting the function to reach about 4 when I'm here, right? So this limit is 4. Okay, so even if our function isn't defined at -2, we still have a limit there. Okay. Let's do the left-hand or the right-hand side. All right, as I am plugging in numbers closer and closer to -2 on the right-hand side, what are the y values approaching? 4 again, good. Okay, so we have a two-sided limit. We have a left-hand side, right-hand side. The limit as x approaches 2 of g of x is equal to 4. Okay, so even though our function had a circle at this point, and it wasn't defined at -2, the limit will still exist at that point because it's what we expect the function to be. It's not what the function is, it's what we expect it to be. Okay. Any questions so far? All right, might be overkill, but let's do one more. Okay. Let's take a look at this graph. Very, very, very similar to the other ones. How is this graph going to be different than example 2 and 3? There's 3 of them, okay. We still have 4 and x squared when we're greater or less than 2. So we're still gonna have 4, we're gonna have our parabola, right? So we're gonna have our parabola. Oops.
2, not -2.
Oh, I'm sorry. Okay, let's modify this question real quick. Thank you for that. Let's add a negative and a negative here. Sorry about that. Okay, just to prove a point here, but nice catch. Let's add negatives to our constraints here. Nice job there. All right, let me continue drawing my parabola. I'm sorry I confused everyone. Okay. Okay, so we got our parabola, we got our straight line at 4. Am I gonna have a circle, closed in circle or open circle at 4? It's gonna be open, right? Because our function isn't saying that x is less than or equal to -2 or greater than or equal to -2. Okay. What else am I gonna have? Alessandra?
It's because there is no value there, except because the value is actually at 5. Because
Okay.
when x equals -2, x actually equals 5.
So what should there be on the graph at
There
-2?
should be a full circle.
There should be a full circle at 5. Do you see that, Alessandra? Nice. Okay, so this is what this graph looks like. It's basically telling us that, okay, we're going to ignore everything when x is -2. And when x actually equals -2, we're going to have a dot here. Okay. Does that make sense? Cool. Okay, so let's just figure out what the limit is at -2 again here, okay? Oh, before we do that, what is g of -2? 5, right? The function is actually 5 at -2. Let's talk about the limits. Let's talk about, okay, as x is approaching -2 from the left, so we're getting closer and closer to -2, what is the y value doing? What are we getting closer to, Cole? It's getting closer to 4, right? This is what we are expecting our function to do based on previous behavior from the left of -2, right? So our function is getting closer and closer to 4. Does everyone see that? Cool. Okay, quickly, what about from the right? Where are we getting closer to? 4, good. So what is the limit as x approaches 2? 4, good. Okay. So basically what we're seeing is it doesn't really matter what the function is at -2 or any point. The limit is based on behavior to the left and to the right. Okay, so what we're expecting the function to take on, not what the function actually is. Okay, so I have here the limit of a function does not depend on whether the function is defined there or not, or even what the function is at that point. Okay, any questions so far? All right. Okay, we have another example here. Example number 5. Let's draw this function. We have b of x is x when x is less than 1, and it's 2 when x is bigger than 1. Okay, so let's focus on the point 1 here. We know that the graph is kind of split. So everything before 1, the graph does something. Everything after 1, the graph does something else. Let's go below 1. So let's talk about x when x is less than 1. X is a constant function, right? So we can draw this graph pretty easily. Okay. It's going to look like a straight line if I can draw one. Let's see. Okay. And are we going to have a closed circle or an open circle at 1? I heard closed and I heard open. It's going to be open, right? Because we have a less than sign, not a less than or equal to sign. Oh, did you have a question?
No.
Oh, you figured out. Okay. All right. Okay, so after 1, it says b of x equals 2, which is a identity, or gosh, a constant function, right? So we're gonna look like a straight line at 2. Is this gonna be closed or open at 1? Gonna be closed because we're greater than or equal to 1 here. Okay, so this is my graph. Any questions on how I made the graph? Perfect. Let's talk about limits here. What is b of 1? 2, right? The function is actually, if I plug in 1, the function is going to give me 2. Okay. Let's talk about the limit as x approaches 1 from the left of b of x. Okay. So what this means is as the x values are getting closer and closer to 1 on the left-hand side, what are the y values getting closer to? 1. Good. So the left-hand limit is 1. Let's talk about the right-hand side. Okay, so as the x values get closer and closer to 1 on the right-hand side, what are we expecting the function to be? 2, good. Okay, is there a two-sided limit here?
No.
No, right? Because the left-hand limit is a different thing than the right-hand limit. What we say is the limit as x goes to 1 of b of x does not exist. D and E. Okay. Any questions on this example? Okay, I think we're doing pretty good. I do have a definition of the two-sided limit if you ever want one. We say that as the input gets closer and closer to a on both sides, there's one output that the function approaches, if you ever wanted a formal definition. Okay, let's do something that you might see similar on your quiz. We've got this big graph here, okay? This is a very big piecewise function. I would never expect you to graph a huge function like this. It's a little bit overkill here. But we got this graph. We have some open circles, some closed circles. Let's try to find some limits here. Okay. So part A, we want to find the limit as t goes to -2 from the right. So let's find -2 first. That's right here, right? We want to find the limit from the right. So as we're plugging in x values closer and closer to -2 on the right-hand side, what's that limit going towards? 2, right? The y value is approaching 2. I know it's not very close, but close. Okay. How confident do we feel with the rest of these? Pretty good. How about this? I'll give you 5 minutes to work on these. You can work together, talk among yourselves. I will be around to see if you're on the right track. Do some of these. Okay. Let me try to get names right. I think I got John to write up part B, right? Do you kind of want to show your thought process here?
From the left, it never hits 1, and from the right, it never hits 3. They're both gaps, but if you actually plug in the 1, it'll be 2.
Yeah. So I like at the end of your explanation, it doesn't really matter what the left and the right are doing, right? Because this question is asking us to plug in 1 into the function. Now, there's an open circle here, open circle here. The function doesn't actually exist there. The function takes on the value 2 when x equals 1. Any questions on part B? All right, what about part C? We have the limit as t goes to 1 of m of t. Who wrote that answer down? Oh gosh, Jackson? Okay, Jackson, do you want to kind of explain your process here?
Yeah, so as it approaches 1 from the left, it's 3, and as it approaches it from the right, it's 0. So since they're not the same, we'll have the two-sided limit.
Perfect. Any questions on what we did here? Okay, so when you're given a two-sided limit, you're trying to solve it graphically. Ask yourself what the limit is from the left. Ask yourself what the limit is from the right. If they don't match, the limit doesn't exist. Okay, nice job there. Part D, I forget who I asked to write that one up. Was it Troy? Yeah. All right, do you want to kind of give us an explanation here?
So it's when you're approaching 1 from
left side,
Mhm.
and it's basically approaching that dot that's way up at high at 3. So that line is approaching 3. So,
Perfect, right? As we're going from the left and we're following the function, we're expecting the function to be 3. Even though the function is 2 at x equals 1, we're expecting the function to be 3 as we go from the left. Okay. Any questions on part D? All right, part E. Who did I ask to write this one up? Was that Maddie? Do you want to take us through this one?
So for the function, we don't have one so you follow one on each side and then flip it.
Perfect, right? The limit from the left is 2, right? Because as we plug in x values closer and closer to 6, we're getting the y value 2. Also from the right, the function does the same thing. So we're expecting the function to be 2, even though the function is 1 at x equals 6. Okay. What about part F? Was that Zach?
Yeah, so when you're approaching from the right, going to x equals 4, you would expect it to be 2 because that's the only line that's actually approaching from the right specifically.
Perfect, right? We're expecting that function to be 2. If we follow the function as it gets closer and closer to 4 on the right, we're expecting it to be the y values to be 2 because all the y values to the right are 2. Okay. Any questions on these graphical limits? Do we feel confident doing graphical limits? Okay, I do have some practice up on the My Classes page. So if you want to do a little bit more, I think I have 2 worksheets on that. These do take a little bit of practice to get the hang of, but I think we're okay on the concept. Cool. Okay, let's flip our page here. I have 2 more types of limits that we haven't talked about yet. This is an example. We have 1 over x squared. We know what that graph looks like. It's the graph that has these asymptotes. In particular, we have the y-axis as a vertical asymptote, right? So we call this a vertical asymptote, right? On the other hand, the x-axis is a horizontal asymptote in this graph. Okay. Okay, what does an asymptote mean? Yeah, the graph gets really, really, really close to it, but it never actually touches it. So we actually don't have a y value for x equals 0, for example. Okay, looks like we want to find the limit as x approaches 0 of 1 over x squared. Well, we have a graphical limit. Let's do the left-hand and right-hand side first. So let's do the limit as x approaches 0 from the left of 1 over x squared. Well, as I'm plugging in values that get closer and closer to 0 on the left-hand side, what is our graph doing? It's going infinitely. It's actually going to positive infinity. We have negative infinity on the bottom. It's getting really, really, really big, okay? Because it's getting super, super big infinitely, we're gonna say that this limit equals infinity, okay? It's getting really, really, really tall. Okay, let's go from the left-hand side or from the right-hand side. Okay, as we're getting closer and closer to 0 from the right, where's our function going? Infinity, right? We're getting closer and closer to positive infinity. Okay, so because the left and right limits match, do we have a 2-sided limit? Yes, right? The limit as x approaches 0 of 1 over x squared, that equals infinity. Okay, so infinity can be an answer to these limit questions. Yeah.
wouldn't positive infinity wouldn't positive infinity be the answer for anything with an exponent that's multiple to in the denominator?
Well, what about this one? Negative 1 over x squared. Yeah, that graph would look like this, and the answer would be negative infinity. Yeah. But good question. All right. Any other questions? Perfect. Okay. Let me just show you one more. Here's a function. You could probably figure out what the function is here, but let's just not talk about that. We want to find the limit as x approaches 2, because that's kind of where the graph splits off. Let's do the left and right hand limit here. So the limit as we approach from the left of our function. Now, remember, this is talking about as the x values get closer to 2 on the left. Where's our function going this time? Negative infinity. We're getting really, really, really low infinitely. So we're getting closer to negative infinity here. Okay, let's talk about from the right. What's our function doing from the right? Where are we getting closer to? Positive infinity. Okay, what's my two-sided limit? Doesn't exist, right? So it doesn't matter if we have infinities or numbers or anything. If the left-hand side and the right-hand side don't match, then our limit doesn't exist. Now, to be a little picky with notation here, when something doesn't exist, I don't write an equal sign because equals just mean is. Equals just means is. We usually don't say a limit does not exist. The limit just doesn't exist. So I don't put the equal sign. I won't mark it wrong if you don't put the, or if you put the equal sign, but some people get nitpicky about that. Okay, I'm going to talk about two more types of limits that we might look a little funky here. Here we have this function, the sine of 1 over x. I would not expect you to actually graph this because it's kind of impossible to graph. But I plugged this into my computer and this is what the graph looks like. Okay, so it's got some stuff going on to the left, to the right. Towards 0, it's actually like having infinitely many of these like oscillations that we call. So I'll write that out, oscillations. And basically what it's doing is it's kind of bouncing up and down between -1 and +1 a bunch of times in the middle, okay? Okay, this is an example of, and I'm not even gonna do left and right because you can kind of see what's going on here. Towards 0, this is an example of something that doesn't actually exist because we're going in between -1 and +1. The function's not getting closer to anything as we hone in on 0. Okay, so before we'll go back to talking about this a little bit later. This is an example of something that doesn't exist, okay? And I'm gonna give you another example before we go back to this example, okay? Here's another example. We have g of x, which is x times sine of 1 over x. Let's talk about this function. We still have these oscillations, but they're doing something a little bit different. So we still have oscillations. Let's talk about the limits here. Let's talk about the limit as x goes to 0 from the left of g of x. Okay. Well, what do you think the function's getting closer to as we hone in on 0 from the left? It's getting closer to 0, right? Okay, what about from the right? 0, right? So this limit actually does exist, okay? The two-sided limit is 0 because the left and right-hand sides equal. What made these two functions different? Why was one of them 0 and one of them didn't exist?
One was being multiplied by the x.
One's being multiplied by the x, yeah, and the x is actually making the function zone in on a particular point, right? So sometimes when we have oscillations, we have something that doesn't exist because the function is not getting closer and closer to something. On the other hand, if we have oscillations that are kind of zoning into one point, we still can have a limit. Okay. Any questions on these two examples? Okay. I think we have enough time to start some limit laws. Does everyone feel confident with doing graphical limits? Sounds good. All right. So I'm literally going to pass out these limit laws, mainly because I don't feel like carrying this to class next time. Okay. So far we've talked about finding limits graphically, right? Basically, the process we've done to find limits is to graph the function, find the limit from the left, find the limit from the right, and then if they match, then the limit exists. That's what we've done so far, okay? Now, in the real world, maybe graphing things might take a little bit too much time. Maybe we don't have a calculator that gives us the graph. And maybe we just have something that we want to find the limit a little bit more quickly, right? This is where these things called limit laws come along. when we have functions that are pretty basic that we can work with, we don't actually need to graph the function first, okay? And we're gonna start working towards different types of functions that we can find the limit of. Okay, so most basic type of function we call the constant function. It's a straight line, okay? This is an example, or the notation for a constant function is f of x equals k, okay? Now I have an example of this function up here. What's k in this example? 3, right? Okay, so it's literally a straight line at the y value 3. Okay, let me just do an example here. Let's say I were to find the limit as x went to, I don't know, 1 of 3. What would that limit be? 3, good, okay? Let's try to generalize this to finding any limit, okay? If I wanted to approach any value a instead of 1 of this function k, what would the limit be as x approaches a of k?
X approaches X.
Not quite. It would be k, right? Because it's going to be the same value as whatever the function takes on. Does everyone feel good about this? Okay, so this is an example of a limit law. Anytime you see a limit of a number, so 3, 5, 7, the limit is literally going to be that number. Doesn't matter where it's going towards, going to be that number. Okay, let's talk about a different one. We have the identity function, the second least complicated graph. F of x equals x, the identity function. Let me do an example here. Let's do the limit as x approaches, I don't know, 5 of x. What's that limit going to be? That'd be 5, right? So in this case, a is 5, x is our function. In general, what's the limit as x approaches a of our constant or identity function? Not x, but a, right? It goes to whatever we're going towards. So this is actually going to be a. Essentially, we're just plugging it into the function. Does everyone see that? Good. Okay. So we have 2 of these things called limit laws. Okay. Anytime we're taking a function of, the limit of a constant, it's just the constant. Whenever we're taking the limit of x, we're just plugging it in. Okay. Now, what I really want to get towards is I have more functions than the constant function and the identity function. I really want to go towards the line mx plus b, maybe I can find the limit of this. So let's just talk about 2x. Okay. Let's say I wanted to find the limit as x approached, I don't know. Let's just keep it general. A of 2x. What do you think we can expect this to be?
2A.
2a, right? Just plugging it in, okay? In general, it doesn't have to be 2, right? Anytime we have k times x, we can bring that k out, okay? So this is k times the limit as x approaches a of x, and we're essentially plugging in a. Okay, so whenever we see a constant times x, we can also just essentially plug in to the limit. So plugging in. Plugging a into x. Okay. So I just have kind of a summary of what we found here. When k is a constant, some sort of number, the limit as x approaches a of k is itself k. We can just plug in a into x, and any sort of constant we can either take out of the limit or just plug in a as well. Okay. Any questions so far? All right, I'm trying to think about, you know what, I think I'm going to let you go because the next thing is a little bit long. So I'll let you go. I will see you tomorrow, and we'll pick up on limits and the quiz review tomorrow.